Welcome, this is Dr. Alim Gable, and we're doing independent events. Other topics to follow we'll be doing later on in coming videos. We're doing combined experiments, permutations and combinations, Bernoulli Trials, and then we'll do Moivre-Laplace and Poisson approximations. But for now, we're doing the first part, which is the independent events. Independent events are defined in the following way. We say that two events, A and B, are statistically independent. There are other forms of independence. We are focusing on the statistical independence. The probability of one event is not affected by the occurrence of the other events. So probability of A, given that B is true, the condition on B does not change the probability. So probability of A given B is just like the probability of A itself. So knowing that B occurred does not change the probability. And similarly, we can say the probability of B given A, or conditioned on A, given that A occurred, if they are independent, then this is equal to the probability of B. Let's say you and your brother, you're trying to buy a t-shirt, and we're looking at the color here. So the probability that your brother got a blue t-shirt does not mean that you're going to buy a blue t-shirt. If you are independent, then you are not affected by his decision. And knowing what color your brother has selected does not change the probability of what you are going to select, assuming that you are independent. If this is not true, then we say that your selection, the event of your selection, is dependent on what your brother has chosen. Okay, mathematically, we can say the following. Now, this is event A, and this is event B. Mathematically, we say that the two events are independent. I'm using colors here just to make things easy for you. So the event A is marked with red, event B is marked with blue. So they are independent if the following conditions hold true. We cannot see the independence directly from the Venn diagram, because the Venn diagram does not represent directly the probabilities. It just shows the sets and how they are related. So the mathematical condition is that if the probability of the joint event, the intersection, equal to the multiplication of the individual probabilities, then we say that the two events are independent. So the probability that you choose blue and your brother choose blue t-shirt, the joint, if it equals to the probability of the multiplication of the individual probability, that your brother choose blue and you choose blue, then we say that the two events are independent. If the intersection probability equals to the product of the individual probabilities. Of course, we have to exclude the case of individual probabilities equal to 0, because that's going to give you the obvious answer. Now, we can use this fact, or we can prove it. Now, if A and B are independent, remember the conditional probability of B given A, equal to the intersection, probability of the intersection, divided by the probability of the condition. If you are not sure, you can go back to our video about conditional probabilities. Now, if this is true, if the two events are independent, then we can go from here to here. We can change the probability of the intersection to the product. And then, of course, this is going to cancel, and what remains is the probability of B. So probability of B condition on A is just the probability of B. Knowing what your brother has chosen for his color as a t-shirt does not change what you're going to do. Alright. Now, we can also show, logically, if A and B are independent, then we can also show that B is independent of A complement. If knowing that your brother has chosen a blue shirt does not change what you're going to do, then also knowing that your brother does not buy, this is the complete, a blue t-shirt, does not help us know what color you're going to choose, because they are simply independent. We're going to show this just for fun using some math. So we're saying here, take this out, the probability of B intersection with the universe. Of course, the inverse now is shown with blue. The inverse, of course, we can write it as A union A complement. The inverse, the external rectangle, is made of a set and its complement, what's outside. So this gives you S. Now we can use the distribution property to go from here to here. Probability of B intersection with A, and probability of, there is no probability yet here, it's just set union B intersection with A complement. So to go from here to here, we use the distribution property. Now we can further say that, of course, take probability of both sides. It's equal to the probability of B. Okay, these are of course disjoint because you are intersecting B with A, which is basically this, and B with this term is B with A complement, which is this remaining part of B. So B is made of, if you allow me, one part here and a second part here. That will give you the overall B. So basically now we're saying if you take probability of both sides, because these are 1 and 2 are disjoint, we can just add their probabilities. And now if we solve for if you assume that A and B are independent, then we can replace the intersection with the product. So I'm just going from here to here. Okay, I just got the red term on the side. Then we have probability of B here. This is going to go on the second side with a minus sign. Utilizing the independence probability, okay, because they are independent, I can just have the product. So now take B as a common factor. We get 1 minus probability of A. Of course, 1 minus probability of A is nothing but B probability of A complement. Okay, now we can see here that we have just proven that probability of A, probability of B, just to show the complement here, probability of B intersection with the complement is also equal to the probability of B times probability of A complement, which means they are independent. So to summarize, if two events are independent, then of course one event will be also independent of the complement. A complement and B are independent. Started with A and B are independent, we have shown that A prime or a complement and B will also be independent. So to summarize in this slide, we have defined what independence is, and we have shown a very important mathematical formulation, which is shown here, the probability of the intersection equal to the product of the individual probabilities. Of course, probability should not equal to 0. Now, there are here some comments about independence which we need to address. Look at the diagram here. Look at the Venn diagram here on the side. Can you conclude that these are independent or not? We cannot directly, as I said, from Venn diagram find independence. So we need to look at the condition of independence. The condition of independence is just sufficient. Okay, it's not just necessary, which means if this is true, there are no other conditions needed. You automatically can conclude that the two events are independent. Of course, this is called sufficient condition. Now, why do we need independence? You know, it makes things very easy. If you want to investigate things, like the example we said, is my GPA correlated, is my GPA or is my grade dependent on my roommate grade or not? Okay, so I need to know these details in life. In many cases, we make things simple by assuming they are independent. Usually we are not proving it per se, but we have to use our common sense. For example, somebody is in a different country buying his t-shirt and is not connected to you. You can fairly assume that your color is independent of what he's going to do. But we have to be careful because sometimes we made assumptions that prove to be incorrect. So we always need to go back to the math proof. Okay, now for positive probabilities, probability of A positive, it's not equal to 0, similarly for the case of B, then we have to observe the following. if the two sets are disjoint, are they dependent or not? Remember, we called the two sets being disjoint, we call them also mutually exclusive. Here is a very common mistake. If these are not intersecting, this does not mean that they are independent. In fact, it means they are fully dependent. So if there is overlap, we are not sure, we have to prove. But if they are disjoint, then automatically we conclude that they are dependent. Why they are dependent? Because if you are in the set, if this is true, if you know that your choice falls inside here, then you automatically know that your product must fall inside. There is no overlap. If I choose a blue color, then he's not going to choose a blue color. If I use a green, why? Because my choices and his choices are separated. And this is called full dependence. Usually, we get tricked because if you see them that they are disconnected, we say they are independent. No, it's exactly the opposite. If they are disjoint, then we can conclude that they are fully dependent. I'm writing this down. Here is an example of mutually exclusive and dependent. So if the intersection is equal to 0, if the probability of the intersection equal to 0, or the intersection equal to phi, then we call them mutually exclusive. If the intersection equal to the product, we call it independent. So knowing that there is no intersection, just tell me they are mutually exclusive and they are dependent. But if the probability of the intersection equal to the product, we call it independent. Now, so for two events to be independent, their intersection must not equal to phi. They should not belong to this example. Because if the intersection equal to phi, then as I said, it's fully dependent or dependent. Alright, so having one exclude the other. Now let's start an example. Remember the cards we use for playing? We have a total of 52 cards. Here is one set. There are 4 different colors or 4 different types. We have 2 reds, 2 blue, 2 black. But here is one set. Okay, we have A, 2, 3, 4, up to 10, and then we have the Jack, Queen, and the King. So these are 13 times 4 give you 52. So we define 3 different events. Selecting a Jack, I am selecting a King, A, and I'm demonstrating this here, as you can see. Selecting a Jack or Queen, we have 8 possibilities. Or selecting a heart, there are 13 of them, from A to 10, and then we have the Jack, Queen, and King. So what's the question? The question says find the probability of A, probability of B, probability of C. And then we have some additional parts. Let's start with this one here. What's the probability of A? Simple. We have, assuming of course fair draw, we have 4 out of 52. And then we have 8 out of 52. And then finally we have 13 out of 52. So we can write this in the following format. Of course you can simplify the last one to 1 over 4 if you like. We can say that this is, for example, we can simplify all of them. This is clearly 1 over 4. That's the easy part. Now let's go into our business here. It says find the probability of the intersection A and B. You can see here that there is no common things between A and B. Okay, this is A and this is B. So you can tell that the probability of this is going to be 0. And then probability of intersection between A and C. If you look at A and C, what's common is only one term here, the King and the heart. So we get 1 over 52. And then probability of interaction between B and C. So I think here it's clearly we have 2 possibilities. We have these 2 here. So this is going to be 2 out of 52. Now that's the easy part. Now it says test for independence, for dependence or independence. How do we test? Okay, is A independent of B? Is B independent of C? Let's do the test. Now, according to our test, we're going to test the following. For example, if you want to test intersection of A and B, you need to take this number and multiply them. Am I going to get the same answer as 0? If yes, we call it independent, otherwise they are independent. Okay. Similarly, we'll do all of them. So let's start here. These are the numbers that we just calculated before. So we have 0, 1 over 12, 52, and 2 over 52. To test independence, we're going to check by multiplying the numbers here. You can see that these two numbers are not the same. So they're not equal. So this means they are dependent. A and B are dependent. If you know that already you are following here, you're going to change the probability because they are exclusive. Then also mutually exclusive. Also we do the same for the others, probability of the intersection. You multiply the individual probability A times C, and you find out that they give you the same answer. Similarly for the last case, B and C are independent. So knowing that it's hard does not help me change the probability. It's always going to be 1 over 4. So we conclude the following. A is independent of C and B is independent of C, but A and B are dependent, because the test for dependence is, does the probability of the intersection equal to the multiplication of the individual probability or not? You can pause this, and if it's not clear, and you think about it again. But now we're going to proceed. Alright, now multiple events. Now we look at the case of independence of multiple events. I'm trying to illustrate this in the diagram here. So we have set A1, A2, and A3. They could be all A4 and so on, but 3 is just to show the idea. Now it says here 3 events A1, A2, and A3 are independent. Then how do we prove this? If this is the case, assuming of course the individual probabilities are not equal to 0, okay, we have to show independence by pair. Okay, so these are the pairs. We are proving here the independence by pairs, which means A1 and A2 are independent. Their intersection probability equal to a product, and we have 3 pairs here. But mind your steps, this is not enough. We have also to show that the intersection of all of them equal to the multiplication of the individual probabilities. So here we are saying, as a comment, independence by pairs is not sufficient. All combinations must be satisfied. Any combination, all of them. Okay, so I'll give you an example where they could be independent by pairs but not independent at the end of the day. So it says we are choosing an example. We're choosing a number between our sample space, which is here 1, 2, 3, or 4, and those are event of selecting 1 or 2, 2 or 3, 1 and 3. So of course we have total 4 numbers. You can tell that the individual probabilities of these events is going to be 1/2, right? Because we have 2 numbers in each of them. So let's look at the pairwise independence. Okay, if you look at the pairwise independence, probability of A and A2, it's here and here, probability of the intersection. You can see that there's one common term, which is 2. So probability of being here and here, it's only one number, so it becomes 1/4. So probability of A1 intersection with A2, which means the common number is 2. So we have only one choice, 1 out of 4, because we are selecting this option. Now, does it equal to the individual multiplication? Yes, because this is 1/2 and 1/2. If you multiply them, you get also 1/4. So if you try all of them, you get that they are independent. But if you look at the joint, what's the probability that our number falls in all of them? A1, A2, and A3. You can see that it's clearly 0, but it does not equal to the multiplication of the individual, because 0 does not equal to 1/2 times 1/2 times 1/2, which is 1 over 8. They are not equal. So because of this drop, because the intersection of all does not hold, we call A1, A2, and A3 not independent, or if you like, dependent. Okay, don't get confused, because we are negating or taking the negative of a negative, which becomes positive. Here are some facts. Any combinations, if A1, A2, and A3 are independent, then any combination would also hold true. For example, A1 and the intersection of A1, A2, and if there is another set defined to be the intersection, they are also going to be independent. And if they are all independent, also A1 should be the independent of the union. Any combination you come up with, they will be independent from each other. So to summarize, in this slide we have shown that if you have more than two events, multiple events, then we have independence by pairs, which could be true or not. And even if it's true, it's not enough to prove independence for multiple events. We have to look at the intersection of all. And if we have four, we have to take two at a time, and then three at a time, and then all of them at a time. All right. So more comments about independence multiple events. Here are some few more comments. If n events are independent, then any one of them is independent of any other events. Union, intersection, complement, whatever you want. And then, of course, if A is independent of A2, we have shown that A is also going to be independent of the complement. If they are independent, this makes our analysis easy, because intersection can be changed into product and probabilities. So I can go from here to here. I'm changing this to product. And also in the next step, I'm changing the second term into product. For the second example, where we have union and intersection, the intersection is now changed into product. For those, of course, for this to be true, we have to assume that all of them are independent. As I said, pairwise is not sufficient. Okay, example, and then we take a practice. Example says drawing 4 A's with replacement and without replacement. I have the cards, and I'm trying to draw 4 cards. What is the probability that I will get 4 aces? 4 aces? Or what's the probability that I will do that with replacement? I am returning the first card, or the card that I took, or without replacement. Now, here are the 4 cards. What's the probability that somebody will draw 4 and they're going to be all aces? With replacement, if I return the card, it means the events are independent. The first event, I'm returning the card, I am putting the card back and starting over. So this is going to be the intersection of having first ace, second ace, third and fourth. It will be the multiplication of the product. Okay, so every one of them, we have 4 aces in the cards. So we have 4 over 52 multiplied by 4 over 52, which means raising to power 4. If you execute this calculation using calculator, you get 3.5 times 10 raised to power minus 5. It's going to be totally different if we don't replace, because if we don't replace, if we keep the card out, then there's going to be some dependence. Okay, now, for example, without replacement, the probability of having 4 aces equal to the probability of the first one being ace, which is 4 over 52. But there is some dependence. I want the first one, the condition on the first one being A. So what remains is 3 aces out of 51, because there's already one game card out. And then the third probability, condition of the 2 before being aces. So we have 2 out of 50. And the third one, probability of A4, given that A1 intersection with A2, A3, which means the previous 3 ones are aces. Then we have 1, because what remains is only 1 ace, divided by 49, the remaining number of cards. You can see this number is totally different than this number. Returning the card make the events independent, so we can use a simple multiplication. But not doing that, we have to use conditional. And you know, remember the relation between condition and joint. So this is general, and this is in the case of independence. Now let's conclude with the following problem. Please write your answer down in the comments. It says, consider the experiment of throwing 2 fair dice. Let A be the event that the first die is odd, and B the event that the second die is odd. and C be the event that the sum of the two numbers is odd. You can write this into a matrix, of course. So odd means we have either 1, 3, or 5. Okay, and you can look at all scenarios, define A, define B and C, and then tell me whether they are dependent or independent and prove your answer. Please share your answers. Find the probability of A, write it down. Find the probability of B, write it down. Find the probability of C. Okay, and then find the pairwise dependence, prove it or otherwise, and share your answer down please in the comment section. Thank you for watching, and we'll see you in coming videos.